A very good morning, students. Today we'll be reading about precipitation. Precipitation has been defined as water in liquid or solid form falling to the earth. According to Foster, precipitation is deposition of atmospheric moisture and is perhaps the most important phase of the hydrological cycle. Well, the objective of this lesson is to make you understand what is precipitation, what are the forms of precipitation. Precipitation is any liquid or frozen water that forms in the atmosphere and falls back to the earth. It comes in many forms like rain, sleet and snow. Along with evaporation and condensation, precipitation is one of the three major parts of the global water cycle. It may be noted that the only process capable of the bringing about cloudy condensation and the resultant precipitation from excessive air masses is the adiabatic cooling. But at the same time, is equally true that not all condensation, even in the ascending currents of air, is followed immediately by precipitation. Even though all clouds contain water, some produce precipitation which others do not. In certain cases, precipitated moisture does fall from the clouds, but it gets evaporated in the atmosphere before actually reaching the Earth's surface. Only when the cloud droplets, ice pellets or ice crystals grow to such a large size as to overcome the normal buoyancy and updrafts in the atmosphere does the precipitation occur. It means that some special process must operate in a cloud from which precipitation falls. Precipitation forms in the clouds when water vapor condenses into bigger and bigger droplets of water. When the drops are heavy enough, they fall to the earth. If a cloud is colder, like it would be at the higher altitudes, the water droplets may freeze to form ice. These ice crystals then fall to the earth as snow, hail or rain, depending on the temperature within the cloud and at the earth's surface. Most rain actually begins as snow high in the clouds. As the snowflakes fall through warmer air, they become raindrops. Particles of dust or smoke in the atmosphere are essential for precipitation. These particles, called the condensation nuclei, provide a surface for water vapor to condense upon. This helps water droplets gather together and become large enough to fall to the earth. A common misconception is that when the rain droplets fall, they have a teardrop shape. In fact, smaller raindrops, ones that are approximately 1 millimeter or 0.039 inches across, are almost perfectly spherical. Larger raindrops, 2 to 3 millimeters or 0.078 to 0.118 inches across, are also round, but with a small indent on their bottom side. They look more like kidney beans when falling to the earth. Very large raindrops, larger than 4.5 millimeters, 0.177 inches, have huge indent and look more like a parachute. These extra large drops usually end up splitting into two smaller drops. The indents on the raindrops are caused by the air resistance. Precipitation is always fresh water, even when the water organized from the ocean. This is because sea salt does not evaporate with water. However, in some cases, pollutants in the atmosphere can contaminate water droplets before they fall to the earth. The precipitation that results from this is called the acid rain. Acid rain does not harm humans directly, but it can make lakes and streams more acidic. This harms aquatic ecosystem because plants and animals often cannot adapt to the acidity. Theories of precipitation. The theories of precipitation and rainfall are grouped in two main categories on the basis of processes of formation and growth of raindrops, namely rapid growth of raindrops due to growth of ice crystals at the cost of water droplets. Firstly, the cloud instability theory of Bergeron-Feinsson, also known as Bergeron-Feinsson process or simply ice crystal theory. And then comes the rapid growth of raindrops due to coalescence of small water droplets by sweeping actions of falling drops, and the collision theory or the collision coalescence theory or simply collision coalescence process. Ice crystal theory of the Bergeron. The ice crystal theory tries to explain precipitation. It was propounded by Tor Bergeron, an eminent meteorologist from Norway in 1933. It is also called the Bergeron process after the name of its discoverer. It is based on two special meteorological properties of water. First, the water droplets in the cloud do not freeze at 0 degrees Celsius. In the atmosphere, supercooled water has been observed down below minus 40 degrees Celsius. When water remains in liquid state below 0 degrees Celsius, it is referred to as supercooled. The supercooled water tends to freeze if it is disturbed. Icing of aircrafts which fly through a cloud consisting of supercooled droplets offers a typical example of this phenomenon. Besides, supercooled droplets also freeze when they come into contact with a tiny solid nucleus about 1 micrometer in diameter. This is called a freezing nucleus. Most of the nuclei become active at 20 degree to 25 degrees. However, freezing nuclei are sparse in the atmosphere. Thus, when the ascending air currents rise well above the freezing level, some of the water droplets will be changed into ice, and through sublimation, water will enter into the solid state. According to Taylor, if a single ice crystal is introduced into a cloud of supercooled water droplets, the entire cloud rapidly changes to an ice cloud. This abrupt change from a water to an ice cloud is caused by different vapor pressures existing over supercooled droplets and ice crystals at the same temperature. Now, we have to consider the second special property of water. Over ice, the saturation vapor pressure is lower than what it is over the water. It is to be noted that when relative humidity is 100% with respect to water, it is about 115% with respect to ice. In this case, vapor diffuses rapidly from air to ice crystals so that the ice crystals begin to grow at the expense of water droplets. The growth of ice crystals is rapid enough to generate crystals large enough to fall. While falling from the cloud, the ice crystals grow by intercepting cloud droplets that freeze upon them. Sometimes these falling ice crystals are broken up into fragments which again become freezing nuclei for other water droplets. A chain reaction takes place. These ice crystals by accretion grow further in size to become snowflakes before leaving the cloud. The snowflakes generally melt before reaching the ground and fall as rain. Because of the glaciation of the upper part of the cloud, its cauliflower-like top becomes anvil shaped, so typical of a cumulonimbus. This process occurs when supercooled water and ice crystals exist together. Supercooled water surfaces have a high vapor pressure, pressure generated by water vapor on a water body or air, than ice surfaces. Water vapor around ice crystals have no time to condense, thus go straight for deposition, the solid form. Water vapor moves from high vapor pressure, supercooled water, and deposited to the ice crystals where they freeze and merge with other ice crystals. The ice crystals become heavy, therefore fall, where upon falling experience warm temperatures and melt as rainfall. This process mainly occurs in towering cumulonimbus clouds where ice crystals are mainly located around the anvil, uppermost part of the cumulonimbus clouds, because of very low temperatures, and in temperate and mid-latitude regions where temperatures are low. However, this theory fails to apply to tropical areas where rain can form in low-level clouds without ice crystals. Another assumption is that the collision coalescence process may take place on the melted droplets and rain then falls to the ground. Collision coalescence theory. Coalescence process of rain making was discovered by E.G. Bowen of Australia. This process is applicable only to those clouds which do not extend beyond the freezing level. Until 1940s, it was common belief that all precipitation originated through the Bergeron process. Only light drizzle was supposed to come from clouds located well below the freezing point. If it were true, then substantial precipitation cloud only be generated from such clouds as extended to such heights where temperatures would be much below the freezing point. But this is not true. In the tropics, cumulus clouds with only 2,400 meters thickness start giving precipitation over the oceans. The temperature in the uppermost part of these clouds seldom falls below 7 degrees Celsius. It is therefore true that the ice particles contribute little in the development of the raindrops of sufficient size in warm clouds. The occurrence of precipitation from such clouds involves the coalescence of cloud droplets of different sizes. Since the rate of fall of these unequal particles is different, they collide with each other within the cloud and larger drops grow at the expense of the smaller ones. In fact, the rate of growth of the falling water droplets depends on variables like size and size distribution of the drops and their concentration in the cloud. Clouds made up of exclusively of liquid droplets can generate precipitation only when they contain droplets larger than 20 micrometers. For the formation of these large droplets, giant condensation nuclei are required. These nuclei are provided by such hygroscopic materials as sea salt. Condensation on these hygroscopic nuclei starts even before the air reaches saturation point. Drops that have grown on such large condensation nuclei become relatively larger. Since the rate of fall is size dependent, the larger drops fall faster than the smaller ones. As such, they collide with the smaller droplets and coalescence. In clouds with great vertical thickness and abundant moisture, cloud droplets are repeatedly carried upward and downward by the ascending and descending air currents. Hence, these drops quickly reach the required size. According to Riel, the following conditions are helpful for the growth of the droplets to required raindrop size. Initially, few condensation nuclei should be present so that there are not too many competing for the available water vapor. Size of the nuclei should cover a good range so that different fall velocities will develop. If a cloud contains only very small droplets of uniform size, there will be colloidal stability in it and cannot yield precipitation. This is no, because in such a case, all the droplets will descend slowly at a uniform rate. Hence, there shall exist little chance of collision among the drops. Besides, for the development of a single raindrop, it will take time much for about 1 million cloud droplets to coalescence. As regards the required size of the raindrops, it is to be noted that water drops must have a diameter more than 100 microns even in humid air. According to Riel, a drop of 500 micron diameter would hardly take 10 minutes to reach the ground from a cloud base 100 meters above the Earth's surface. But a drop with a diameter of only 10 microns would take at least 50 hours to cover the same distance. A radius of the 500 microns has been adopted as the minimum size of a raindrop. Below this, raindrops are referred to as drizzle. Most of the cloud droplets are so small that the motion of the air keeps them suspended. Even if these microscopic droplets were to fall, they would evaporate before reaching the surface. It has been demonstrated by the high-speed motion pictures that sometimes mere collisions do not lead to coalescence. Besides collision, electrical attraction between the droplets plays an important role in bringing about coalescence. The colliding droplets have opposite charges, coalescence is easily achieved. The role of electrical attraction in generating precipitation from a cloud has been investigated by Bernard Wonget and Charles B. Moore. Whatever process or processes are at work, a continual supply of moisture to the atmosphere over particular location is the most important condition for ensuring a prolonged precipitation. This theory explains that water droplets big and small in the cloud collide against each other caused by the convectional currents in the cloud. The initial small droplets are not dropped but kept suspended in the cloud until they are large enough to be dropped. As other large water droplets that are still suspended in the cloud collide with small water droplets, they coalescence or join, causing them to become bigger. Eventually, they get larger that they are unable to be suspended any longer in the cloud and fall down. Upon falling, the large droplets are ripped apart by the convectional currents and air friction, which disintegrates them into new droplets which fall as rainfall. Collision coalescence mostly applies to warm convectional clouds in tropical areas. Forms of precipitation. The precipitation of atmospheric moisture occurs in a number of different ways depending upon the temperature of dew point at which the air is saturated and condensation begins, the altitude and the types of the clouds, the atmospheric conditions through which the cloud droplets pass through, mainly in the terms of temperature. The process of adiabatic cooling, that is the cooling either caused by mechanical lifting of the moist air and consequent expansion of the air leading to decrease in the temperature, increasing relative humidity, and ultimately condensation of moisture, or by dynamic lifting of the moist air either by radiation or by frontal activity. If the condensation occurs at temperature above freezing point, that is above 0 degrees Celsius, the precipitation takes place in liquid state, namely rainfall. On the other hand, if condensation occurs below the freezing point, that is below 0 degrees Celsius, the precipitation takes place in solid state such as snowfall. The types of precipitation include rain, drizzle, freezing drizzle, snow, snow pellets, snowflakes, snow grains, ice pellets, hail, etc. It may be mentioned that generally fog, dew, mist are not considered as forms of precipitation, but some scientists plead for their inclusion under the category of precipitation. Rain. Rain is the most widespread and important form of precipitation. It occurs when there is sufficient moisture in the air and condensation occurs above the freezing point, that is above 0 degrees Celsius. Rain is in fact liquid water in the form of raindrops with diameter of more than 5 millimeters. It is important to point out that one raindrop contains as many as 80 lakh cloud droplets. Raindrops fall at velocity of 200 times greater than cloud droplets. When raindrops become very large and fall down at greater speed, more than 30 kilometers per hour, they split in the transit but give very heavy downpour. Sometimes precipitation occurs at higher altitude from cumulus clouds in the form of rain, but the trails or streaks of such rain coming from the undersurface of the clouds is evaporated in the transit before reaching the ground. Such rain is called virga. Next important form, drizzle. Drizzle is defined as the fall of numerous uniform tiny droplets of water having diameter of less than 0.5 mm. Drizzles fall continuously from low stratus clouds, but the total amount of water received at the ground surface is significantly low. Sometimes drizzles are combined with fog and hence reduce visibility. The drizzle intensity is generally 1 millimeter per hour. Snow is formed when condensation occurs below the freezing point, less than 0 degrees Celsius. The fall of snowflakes is called snowfall. Snowflakes are formed when air temperature is greater than minus 5 degrees Celsius but less than 0 degrees Celsius. In fact, snowfall is precipitation of white and opaque grains of ice. The snowfall occurs when freezing level is so close to the ground surface, less than 300 meters from the ground surface, that aggregations of ice crystals reach the ground without being melted in solid form of precipitation as snow. The next form, snow pellets. Snow pellets having white and opaque grains of ice of spherical shape are formed when condensation takes place around the freezing point. The diameter of snow pellets ranges between 2 millimeters to 5 millimeters. The grains involved in the formation of the snow pellets are so brittle that they break in pieces after being pelted by the ground surface. Snow pellets are also considered as a soft variety of hails. Graupel, a form of precipitation in the solid form, is comprised of ice grains of white color and is opaque or light. The diameter of the graupel, also called as snow grain, is less than 1 millimeter. Ice pellets are, unlike graupel or snow grains, transparent or translucent grains of ice which are formed when condensation takes place below the freezing point. The diameter of the ice pellets is up to 5 millimeters and the shape of the pellets is highly irregular depending upon the conditions of condensation. Ice pellets are in fact frozen raindrops. Sometimes they are also formed when snowflakes are melted and refrozen. Hail. Hail consists of large pellets or spears or balls of ice. In fact, hail is a form of solid precipitation wherein small balls or pieces of ice known as hailstones having a diameter of 5 millimeters to 50 millimeter fall downward, known as hailstorms. Hails are very destructive and dreaded form of solid precipitation because they destroy agriculture crops, claim human and animal lives. The next form, sleet. Sleet refers to the mixture of snow and rain, but in American terminology, sleet means falling of small pellets of transparent or translucent ice having a diameter of 5 millimeters or less. Next comes the freezing rains. Freezing rains or freezing drizzles are formed when the drizzles or very light rain occur below 0 degree Celsius temperature. They are frozen before reaching the ground surface and hence they are called freezing rains or freezing drizzles. They are also called as crachants. Next comes rime. Rime is an opaque coating of tiny white granular ice particles caused by rapid freezing of the supercooled water droplets on impact with an object. Webster Dictionary defines it as below the freezing point. Rime is deposited mainly on the edges and points of objects. Rime is in fact deposit of opaque white and rough textured ice crystals. They form after accumulation of rime looks like cauliflower shaped heap. Now let's recap the important types of precipitation in simple terms. Rain. It's nothing but most commonly observed form. Drops larger than drizzle, 0.02 inch or 0.5 millimeters or more, which are considered as rain. However, smaller drops are also considered raindrops. If in contrast to the drizzle, they are widely separated. Drizzle. Fairly uniform precipitation composed exclusively of fine drops very close together. Drizzle appears to float while following air currents, but unlike fog droplets, it falls to the ground. Quite often, fog and drizzle occur together. Ice pellets or sleet. Precipitation of transparent or translucent pellets of ice which are round or irregular hard grains of ice consisting of frozen raindrops or largely melted then refrozen snowflakes. Hail. Precipitation in the form of small balls or other pieces of ice falling separately or frozen together in irregular lumps. Associated with thunderstorms, individual hailstones are 1/4 inch or greater in diameter. Hail sizes of 1 inch or more are indicative of severe thunderstorms. Small hail or snow pellets. Precipitation of white opaque grains of ice that are round, sometimes conical. Diameters are 1/4 inch or less. Snow. Precipitation of snow crystals that are mostly branched and in the form of 6-pointed stars. Snow grains. Precipitation of very small white and opaque grains of ice. Basically, this is frozen drizzle. Ice crystals generally occurring in very cold regions. They are falling crystals of ice in the form of needles, columns or plates. Also called diamond dust. Ice crystals appear like fog with individual water particles forming directly as ice. The shape of the individual ice crystals causes the light pillar optical effect above the light source. Precipitation refers to fall of atmospheric moisture either in liquid form such as water through rainfall or in solid form such as snowfall after cooling and condensation of ascending moist air after dew point is reached. Precipitation is also defined as deposition of atmospheric moisture either in liquid or solid form. The adiabatic cooling of moist air caused by either mechanical lifting, orographic obstruction and lifting, or by dynamic lifting as a result of radiation, heating and resultant convection and turbulence, and as a result of frontal activity causes condensation and precipitation.